Today we're going to talk about rigid bodies and translations, rotations as well too. This is an example of a sphere. I have cut a slice through it. You see that the center mass is right there. And then we're going to pick a point on the surface. If I pick a point right here, now I've drawn this not right on the sphere because my smartboard thinks it's fun to move stuff around. So just imagine this being right on the circle. If I have a point right there, that's a tangent, that's a tangent, that's a tangent, that's a tangent. That's the direction you'll be going. If for some reason, say we come to a sudden stop, and whatever object's on there is going to fly in that direction. So if you imagine these tangents going all the way around, you can pretty much predict the flow, the velocity, if you will. Now, the rotation we generally look at in terms of omega, where omega is angular velocity. So this is really nothing new with what we have discussed. And remember, in the past we said that omega is equal to the change of angular displacement with the change in time. And generally we had labels of radians per second or revolutions per minute, also known as RPM, anything like that. But that only deals with the rotation part, the actual counting of how many times it rolls around or how many radians it's moving. We can go degrees per second if we want to be old school, which we don't. And at the same time that we follow one of these points on the outside, we focus on the point on the inside. So how is this moving in relation to what's moving over here? And that's where the straight line portion of velocity comes in that we talked about when we were dealing with angular velocity, acceleration, momentum, whatever. So if I were to change this over to just plain linear velocity and watching this moving from here to here, because it's not going to rotate around like these points are, but this is going to be what we call a translational motion here, then we'll just simply take the radius of this circle that we are looking at here times omega. Now there's all kinds of options we can do here. If you go online and see the videos that they have for this, one of the things they can examine is picking 2 points and rotating this around and watching how as this translates and rotates in whatever axis you want, those points are going to stay there the whole time. So I'm just going to make it simple and just deal with the center of mass here. Okay? So we know that there is an angular acceleration because of this is a constant change in direction. Remember, velocity is the change or acceleration, excuse me, is the change of velocity with time, but velocity is also the involving speed with direction. And as you can see, the direction is constantly changing here. So while the velocity may be the same going all the way around, the fact that the direction is changing means the acceleration is changing as well. And so, like if we were to pick a spot where we were to, like I said, stop this thing, pick a point where just stop the roll instantaneously, things are going to fly off in the direction of this set of arrows we have here, or anywhere in between until gravity takes over, which is almost instantaneously, creating your parabolas that we talked about also in a previous chapter. All right, so when we talk about rigid bodies and translations, we're simply looking at the rotational aspect and changing it over to linear velocity. Translation is that linear velocity and distance that we may be examining here. So, let's take an example of this. We have an 11-inch diameter tire. And we are going to roll it at a rate. This is well, we'll come back to that. This is the angular velocity. We said is 7.55 RPMs. Okay, and the question is, what is its translational velocity? So I'll put V sub t for this, for translational. We are given here that we need to do some converting here. 1 inch equals 2.54 centimeters. Okay, so the first thing we need to do is start with this diameter and change it over to radius, because we are going to need to figure out the linear aspect by using that radius. So let's take a quick look at that. 11 inches times, and we're going to convert inches to centimeters, put inches on the bottom, centimeters on top, and then we're going to change centimeters to meters. And according to what we're given here, we know that 1 inch is equal to 2.54 centimeters, and 1 meter is equal to 100 centimeters. And we punch this into our calculators, and we get 2.279 for the diameter. But we don't want the diameter, we want the radius. So the radius then is going to be half of that, 0.279 over 2 is actually 0.2794, which means it's just going to round up the way we would have done it anyway, which is 0.140 meters. Okay, now, that gives us the radius of the tire. We also need to change the omega for this. The omega for this we were given as the angular velocity is 7.55 revolutions per minute. And so we want to change this over to radians per second. And 1 revolution is equal to 2 pi radians. And then we need to change the minutes over to seconds, put minutes on top, seconds on bottom, 1 minute, 60 seconds. So now all the labels cancel out to leave us radius per second. And we're going to punch that out and get that into 3 sig figs. And I get well, let's just go ahead and change it right to VT here. And get, multiply this. Since the 1 radian now we calculate as 0.140 meters. So 0.140 meters per 1 radian. We'll do it that way. That's what I did on the paper. And this turns out to be 0.111 meters per second. So that would be the translational velocity involved here. So I give you some practice problems. This is more of a refresher, but it's a different way of looking at angular momentum and angular velocity and angular distance and all that good stuff. So do the practice problems and have fun.